guys for this last video in the stereochemistry chapter. So we just want to talk about the properties of enantiomers and diastereomers, because so far we talked about, like, on paper, right, structure wise, like what is a diastereomer, what is an enantiomer. Enantiomers are mirror images of each other but different. Diastereomers are different stereoisomers, but they're not enantiomers, right? But what about the actual properties of these things? And the first interesting case that we might talk a little bit more, perhaps in the class, is the thalidomide scandal. And this was a pretty big thing in the 1970s. So here's are the two structures of the thalidomide enantiomers. Here's the dextrorotatory clockwise light rotating enantiomer. Here's the levorotatory thalidomide. And what happened was this drug, the dextrorotatory enantiomer, this is a mild sedative. Oops. And it's also good for as a sleep aid, and also as a treatment for morning sickness. Because of the sedative effect. And now, so as you can imagine, this was a popular drug that was prescribed for pregnant women in the 1970s. But the problem at the beginning was the manufacturing or synthesis process, because enantiomers have identical physical properties and identical chemical properties. It's really hard to separate these two. We'll talk about the separation in a minute, but because of that, really to cut costs, they sold a racemic mixture, in other words, one-to-one mixture of these two enantiomers. Now, that might be okay if the enantiomer has the exact same property, but what happened was that this enantiomer was teratogenic, which we didn't know about that at the time. And so what happened, by the way, the word teratogenic means it causes birth defect. And that's, of course, the worst combination, right? Because this is particularly useful for pregnant women for treating morning sickness, and produces teratogenic effect. And so there were a bunch of these babies that were born with, unfortunately, non-existent, very shortened limbs. And they were called thalidomide babies, and it was a big social issue at the time. Now, why did that happen, right? Let's think about that. So enantiomers, of course, they are mirror images of each other. And what happened, well, sorry, some of the symbols didn't show up very well, but all the physical and chemical properties, like melting point and how it behaves in chromatography, they're identical, right? Like the melting point is the same. The only difference, of course, is that, sorry, this is supposed to be alpha for the optical rotation. The optical rotation would be the opposite sign but the same value, right? That's supposed to be the only difference between the two. However, what happened was that obviously the biological impact effect was different. So why is that? That's because the proteins and DNAs, but especially in this case proteins that these drugs interact with in our body, the protein molecules are chiral. They're made of chiral amino acids, and so that makes them a chiral. When you have two things that are chiral, the interaction between the two is specific, so that the this enantiomer interacts with a particular protein differently than this enantiomer does because they're both chiral. It's kind of like the same thing as if you try to go shake somebody's hand with your right hand, you want them to put out their right hand as well. If they put out their left hand instead, the handshake would be really awkward because your hand is chiral. It's kind of a similar idea, okay? So maybe we could just say that these two interact with proteins which are chiral. Differently. However, in general, chemical and physical properties are identical. Between the two enantiomers. Except for optical rotation. So optical rotation is different, which way it bends the light. But it should be the same value. Or if they're in an environment where there's other chiral molecules, then the two enantiomers would behave a little differently. Okay, so that's enantiomers for you and their properties. Now, diastereomers, they would have a very different properties to begin with, and so that's pretty different. Like for instance, if you compare these two structures, the one on the left, this is called D ribose. When it comes to the carbohydrates, you might notice that the D and the rotation direction, that those D and L designation and the rotation direction, they actually do not match, and that's just a specific naming convention for carbohydrates. And then I hope I don't confuse you, but ribose, this ribose isomer is levorotatory, but it's designated as D because it's based off, biosynthetically speaking, it's derived from the glyceraldehyde. So they're all called the D sugars, and there's something I think you would learn later in organic chemistry or in biochemistry, but all naturally occurring sugars are D sugars, meaning that they're all derived from D glyceraldehyde, but each one can bend the light in either clockwise or counterclockwise, right? So it could be levorotatory, like this ribose case, or dextrorotatory as well. And this other one is also happens to be levorotatory, but this sugar is called arabinose. Unlike the enantiomers, we call them differently because they're really two completely different molecules, whereas both of these up here are thalidomides, just mirror images of each other. These two guys are not mirror images of each other. In fact, the physical properties and whatnot are very different. Ribose melts at 95 degrees Celsius, whereas arabinose melts at 164. So the physical chemical properties are different. Of course, the biological properties are different, but just to show you what D-glyceraldehyde looks like in Fisher projection, it looks like that. You notice that's this part is derived from D-glyceraldehyde, and this one is actually indeed dextrorotatory. this R configuration is kept among all the naturally occurring sugars. Right, so these guys all have the same chiral center here because everything is derived from the D-glyceraldehyde, so all natural sugars are D sugars for that reason. Okay. Now, these two also have different biological properties. The arabinose, interestingly, is an inhibitor of sucrase, which is the enzyme that digests or metabolizes sucrose, which is the table sugar. So basically, it won't let you digest or metabolize or take up calorie from sucrose, the sugar. So in some countries, it's actually used as a diet pill. Basically, no matter how much sweets you eat, that you should not gain weight, and that sounds all great, but comes at a cost. Many people have the side effect of diarrhea. It's not approved for usage in the US, by the way, and last I checked. And this other compound, ribose, is, of course, you might have heard about it. This is the building block for nucleic acids like DNA and RNA. Okay. Now, one other thing I wanted to point out, if you assign the RNS, I forgot to mention this here. I hope it makes sense to you that this is R and this is S. The it's here the fact that it's R assigned and that it's dextrorotatory, that's coincidence. Just because something is the chiral center is assigned as R, it's not necessarily going to be dextrorotatory. So you can't predict that. That's determined from the experiment. Okay. So just from the RNS assignment, you can't predict which way something would rotate light. If you know the rotation of the other enantiomer, then you know that it would be the opposite. But I hope that makes sense. Now, the last thing to talk about, separation of enantiomers, right? Because earlier we talked about how the big problem that this thalidomide compound caused. So, of course, to make this a safer drug for pregnant women, it needs to be separated into the two enantiomers. How would we do that? If enantiomers have the exact same physical properties, then it would seems impossible. But knowing that the diastereomers do have different properties, what we can do, for instance, in this case, let's say we need to separate these two enantiomers somehow. How can we do so? Well, here's one way. Okay, and that is that you make a diastereomeric salt. Okay, so if you add to this a particular diastereomer, like an enantiomer, like this lactic acid. Which of course has that one chiral center. It's a chiral molecule, and because that's a naturally occurring molecule that you can harvest from nature or even technically from your muscle, right? You can obtain this in enantiomerically pure form. So if you mix this racemic mixture of enantiomers with enantiomerically pure material, what would happen is you can form a salt. Remember that this is carboxylic acid functional group. It's acidic. Remember from Gen Chem that amines or nitrogens in general are weak bases, and so for that reason there'll be acid-base reaction, and you're going to have an ammonium cation and carboxylate anion salt. Okay, so this is racemic in the beginning, and then you can make this salt, the mixtures, and the counter ion is the same. So I want you to notice that these two salts have the relationship of being diastereomers, because one of the chiral centers is the same within this salt mixture, but the other chiral center is different. So these are diastereomeric relationship. Right, two different salts have a diastereomeric relationship to each other. Okay, I'm talking about this salt versus that salt. That means that these two can be separated by physical processes like recrystallization. Or chromatography. And after they are separated, if you take off the acid part of it from the salt, then you'll have the two enantiomers that are separated. And typically when you have to separate a racemate, this is the kind of processes you would go through. Okay, we'll discuss the rest in our class. See you then.